This is my drone autonomously transporting a bag of dog poop 20 meters above my neighborhood. You're probably wondering how I got here. Let me explain.
I have a problem. I have 2 dogs, and sometimes I take them on walks.
Okay, I never take them on walks. But when I do, this happens.
Really, Graham? You're gonna make me pick that up, aren't you?
And that isn't even the worst part. Now I have to walk all the way back to my house carrying a disgusting bag of
I bet you're thinking what I'm thinking. What if I could summon a drone to autonomously fly to my location, pick up the poop bag, and return it safely home?
Either that or drop it into a random neighbor's yard. Not my problem either way. For some reason, I thought this would be a silly project that I could finish over winter break. Little did I know, I was about to embark on a 2-year journey that would push me to the breaking point.
I think I'm gonna need a bigger drone.
Now that I've blown all my savings on drone parts, let's put this thing together. Somehow. This is a Pixhawk flight controller. It's going to make this project a lot easier. It handles all your basic drone stuff, like flying. And also GPS waypoints, low battery detection, position hold, RC control. The coolest part is I can attach a Raspberry Pi to it and then send it commands using Python. I'll do that later in the video, but first I think we should try to get manual control working. And done.
All right, first flight test out in the open air. Second flight test out in the open air. Why is it doing that? Flight test number 3. Oh, oh.
The thing about drones is, when things go wrong, things go very wrong. After replacing the 2 broken arms from that incident, I decided to test things in a less risky environment. This was supposed to be the easy part of this project. I finally realized that I had been calibrating the speed controllers incorrectly,
Watch out,
and
Graham.
just
Hey,
like that,
Graham.
Greta was
No.
up in the air and flying around like a drunken sailor.
Yes. Fly, Greta, fly.
Next, I took the drone out to a field and tested some of the built-in functions provided by the Pixhawk firmware. This is the loiter function, which, as you can see, worked super well right out of the box. It could even land itself way better than I could. My happiness was short-lived, however, because then this happened.
What is that motor doing? That seems like a problem.
I found out later that night that one of the motor connections had broken off inside the manufacturer's heat shrink. Little did I know, that would not be the last time I encountered that issue. In any case, I was not feeling too good about strapping a $200 computer to such a crazy chick, but I did so anyway. Now that Greta flies somewhat, it's time to start programming her. In order to do that, we'll need this. It's basically a little computer that... Psst, wait, what? This is an NVIDIA Jetson Nano. It's basically a little computer that can run Linux. You can even connect a keyboard and monitor to it. Isn't it cute? I can program it to send commands to the PixHawk, which will make the drone move. I 3D printed a case for the Jetson so that I can mount it on the drone. I also got this USB cellular module, which has its own SIM card like the one that's in your smartphone. This will allow the Jetson Nano to connect to the internet anywhere that there's a cell signal. That means that I can stream all the telemetry data from the drone to my laptop or phone using a VPN. And it effectively gives the drone infinite range through the internet.
Whoa, what's that say?
We also need to set up obstacle avoidance.
This is what happens to a drone that doesn't have obstacle avoidance.
So how do we make Greta see the giant tree that is right in front of her? There's a couple of options for this. I could use this cheap sonar sensor to detect how far an object is in front of the drone, but that doesn't give us enough information to plan a path around the obstacle. I could use a spinning LiDAR system, but those are expensive, don't work well outdoors, and only provide information in a 2D plane, which isn't ideal for our 3D environment. What if we give her eyes? And by that, I mean 2 cameras. Why 2 cameras? Well, if we have 2 different images taken by 2 cameras placed side by side, then objects that are closer to the camera will appear to change position more between the 2 images. This is a very handy thing to exploit if we want to extract depth information. There's an algorithm called stereo block matching, which slides a window over a pair of images and measures the disparity between them, generating a depth map that looks something like this. What? You're supposed to make this easy. With the GPU-enabled algorithm and the right calibration, I did eventually get a decent depth map generating at about 10 FPS. Now, because we know some camera intrinsics, like the distance between the 2 cameras and the camera focal length, all it takes is some linear algebra to turn our depth map into a point cloud. Not that. No. There we go. Now every pixel has been given an X, Y, and Z coordinate corresponding to the real world. We can feed this point cloud into an obstacle avoidance algorithm provided by the firmware, and then it should handle the rest. Here's that algorithm running in simulation. Seems pretty easy, right? Wrong. This is when the project really started to go downhill. Lesson 1. Nothing in robotics will ever just work. I don't want to bore you by complaining about every single little issue that I encountered, but let me just tell you, whether it be connecting the cameras to the Jetson, building OpenCV with CUDA support, connecting to the PixHawk over serial, running the simulation, or enabling obstacle avoidance in the hexacopter firmware, every little step took me weeks to get working. I remember describing to my friend working on the project was like chewing glass. And considering I was back in school with limited time to work on the project, weeks and weeks started ticking by, and then months. At this point, it seemed like the obstacle avoidance was somewhat working, but I was still having issues with the quality of the point cloud, which meant that the drone would spin in place and meander about like a confused child because it thought obstacles were all around it. So I decided to pretend like that problem was solved and moved on to actually landing on the bag. This means that I have to somehow know where the bag is, and then move the drone to land precisely on its position. If I show you this picture, hopefully you could tell me right away where the plastic bag is because your brain is such a beast. If I show the computer this picture, it sees this. So the best I can do is write an algorithm that looks for a blob of white pixels. But then the computer might think that this bright spot on the sidewalk is a plastic bag. Luckily, this problem was solved like 100 years ago. Instead of writing an algorithm, I'm going to give the computer lots of images of plastic bags, and then it will converge on a giant multi-dimensional function that takes in image pixels and spits out bag locations. In short, I trained a YOLO model on Google Colab for a couple of hours. Unfortunately, the Jetson had a hard time running even the smallest YOLO models, even though that was the whole reason I bought it. So I decided to pretend like this problem was solved and moved on. Lesson 2. Embedded devices are potatoes. I wasn't expecting the $200 Jetson Nano to work as well as my desktop 3070, but everything is so slow. To land on the bag, all I really need to do is control the drone's velocity to keep the bag centered in the frame as it descends. Let's try that.
So, tell us about your adventure.
We are off to test the bag landing. Any number of things could go wrong.
Is this the first time you're testing it?
Yes.
This dude is busy with the silliest project known to man. The poop drone? More like the poop drone.
Okay. Alright, I definitely need to tone down the
speed, yeah.
After this episode, I realized that no matter how low I set the velocity, the drone always jerked violently to the side. Here, you will see what happens when I program the drone to move a mere 0.5 meters per second to the right. This was incredibly frustrating because my code worked perfectly fine in the simulation, and the drone flew stably when I was controlling it manually, but the second I send a velocity command, it decides to crash itself. Lesson 3. Don't try to build a drone when you're living in the middle of a city. Come on, think about these things. In between sleeping through my comp art classes, I would pack up my things, travel down 15 floors in an elevator full of frat guys. Yo. Is that a drone? Yeah. Sick. Why is it named Greta? I don't know. Sick. Drive to a nearby park, fight for a parking spot, wait for the drone to boot up, connect my laptop to my hotspot so that I can SSH into the Jetson, fly the drone, try not to kill any of the toddlers or old men who are constantly swarming me, only for the drone to crash immediately, breaking a leg or an arm or the GPS stand, and forcing me to come a few days later with one line of code changed to start the whole process over again. So here I was, 6 months into this stupid project. Nothing's working properly, and I'm faced with an impossible firmware issue that only seems to affect me and crashes the drone every time I try to make it do anything. Lesson 4. If it ain't working, stop trying to make it work and try something else. It was definitely time for a different approach. First, I switched from PX4 to arduino to get around some of the firmware issues. I also switched from Mavros to a more user-friendly library, DroneKit. Finally, I could control the drone without it crashing. Secondly, I realized that I could buy specially made depth cameras instead of trying to use my crappy DIY stereo PiCam setup. Using one of these bad boys has a lot of advantages. For example, these RealSense cameras come out of the box with perfect calibration, an onboard processor to generate the depth map, and an infrared dot projector to improve accuracy. The obstacle avoidance that is built into arduino is much less sophisticated than PX4. It just accepts a 2D scan of obstacles in front of the drone and then plans a path around them in a 2D plane. That's why I originally wanted to use PX4. So to get the obstacle distance information, I'll just sample the depth map along that scan line. In order to get some 3D information back, I can just use the closest obstacle based on several scan lines. Of course, this didn't work on the first try. Once I slowed down the drone's movement speed, filtered out some of the noise from the depth map, fiddled with the arduino parameters, and forced the drone to rotate fully towards its heading, we were back in business. Now I am 50% confident that the drone won't run into things, up from 0%. I also have a downward facing depth camera which I can use to avoid obstacles while descending and to detect safe places to land. Third, I bought this Coral TPU accelerator, which is designed to run machine learning models in a tiny form factor. I can connect this to the Jetson over USB to essentially offload the computer vision tasks and drastically improve the bag detection inference time. Only one problem. The Coral can only run TF Lite models, so I had to figure out how to train one of those. That was fun, because somehow in the process of installing the TensorFlow libraries, I bricked the Jetson for the second time, requiring me to completely reflash the board. Unfortunately, I ended up with a model that was really good at finding bags in HD images like this, but didn't really work for the sucky top-down images that came from the drone camera. So I was able to use my old white blob detection algorithm, plus some manual work filtering out the bad detections, to quickly create my own dataset of about 500 images, all sourced directly from videos captured by the drone. This approach worked surprisingly well. With this, I was finally ready to perform my first precision landing. I started with this red Tupperware lid as the target. Come on, baby. Come on, baby. Yes. Please. Please. You got it. You got it. Ah. This turned out to be harder than it seemed. Surprise, surprise. But I had a few tricks up my sleeve. First, notice when the drone pitches to the side, the target will move to the opposite direction in the image frame. This will cause the drone to overshoot as it tries to center the target. In order to correct for this, we can draw a right triangle here and solve a trig equation to find this edge. Once we know the distance in meters, we can convert it to image pixels and apply an offset to the target coordinates. Now, the target's position in the image will accurately reflect its position in the real world, regardless of the drone's attitude. Another problem is that there isn't a good way for the drone to know its own velocity. Normally, the autopilot uses a combination of GPS, dead reckoning, and accelerometer readings to guess its velocity, but in a windy and unpredictable environment, this doesn't quite provide the level of accuracy that we need. The cool thing is, given that the target is stationary relative to the world, if we use several image frames taken at known time intervals, we can calculate the velocity of the target relative to the drone. And that is the same thing as the drone's velocity relative to the world frame. Oh, by the way, I never got this part working. Okay, we'll have to do without it. I'm used to game development, where the environment is completely deterministic and you can get the exact velocity and position of every object in the scene at any time. Let's just say I was missing that about now, but I was getting somewhere. Now, if we want to start landing on a bag, then we should probably have a way to pick it up. For the grabber mechanism, I'm thinking something like these two rakes. So I flexed my Fusion 360 skills once again and catted the gripper arms and mounting mechanism. I got them printed, added a servo, and then the whole thing was working like a charm. Landing on top of the bag was significantly harder than landing on the Tupperware, both because I had to get close enough on top of the bag to actually grip it, and because the bag has a tendency to blow around and change shape dramatically while the drone is trying to land on it. The concept behind this algorithm is simple enough. Descend while the target is centered, otherwise set the velocity of the drone to center the target underneath. But to actually get this to work is a different story. A whole bunch of questions arise, like what adjustment speed and descent velocity should I use? What is the threshold to determine when the bag is centered? What is the criteria for triggering the final descent? How should the drone handle losing track of the target? And what's the optimal way to bunch up the bag to maximize surface area and minimize floppiness? And of course, all these parameters might change depending on the altitude. It's easy enough to get the drone to land within 12 inches of the target, but if you want to get within 3 inches, you have to get as low to the ground as possible before triggering the landing. This becomes exponentially harder, because at an altitude of 5 feet, this is what the drone sees. The smallest air at this altitude will cause the drone to lose track of the target completely, and the position of the target is so sensitive to velocity changes that it becomes impossible to keep it centered. I had no choice but to go out in my backyard, fire up the drone, and manually experiment with these parameters and strategies for weeks on end until I thought that I found the best combination. Eventually, it became clear that I was narrowing in on the optimal solution. But despite my best efforts, it didn't look like I could do anything to reach a success rate above 50%. This wasn't good enough for me, so I came up with an idea to use the depth map from the downward facing camera to detect if the bag was hanging from the drone or not. That way, if the drone fails to get the bag the first time, I can make several more attempts until it does. Lesson 5. Streamline testing, or face not so rapid iteration. For some problems, you just have to whack them with a hammer until they work. In these situations, the real bottleneck is the time it takes to test and iterate. This project took so long, partly because testing required being in an open space with a good GPS signal and Wi-Fi connection, a setup I could only find in my backyard over 100 miles from my school. On top of that, I had to contend with the drone running out of battery every few hours, unpredictable weather, and limited daylight hours. Now, I just need a way to send my location to the drone when I'm out walking my dog. I found this template for a drone app on GitHub, which already has features for monitoring the drone's altitude, battery, and location via Mavlink, a standard drone messaging protocol. I can pretty easily extend the functionality of this app to get my GPS coordinates with location services and send them to the drone over the internet using a TCP message. Well, it would be pretty easy if I knew Swift. When the drone receives these coordinates, it will take off and start a mission to fly to the specified location. Since the GPS is only accurate in about a 5-foot radius, I'll have the drone search for the bag in a spiral pattern, expanding outward from the target position. This seemed to work well enough combined with the obstacle avoidance, even when near multiple trees. All that was left was putting everything together and programming the full mission sequence. But things weren't that easy. Throughout this whole process, I was constantly plagued by mysterious issues that brought the whole process to a halt. For example, there was a period where the drone would completely lose yaw control every other time it took off. And then there was the issue where the drone would suddenly lose its ability to maintain altitude and crash. And of course, a speed controller would burn out every now and then, for no apparent reason. Looking back, I'm pretty sure that most of the problems were caused by faulty connections from the speed controllers to the motors. You'll remember this issue from very early on in the project. This was particularly terrible to troubleshoot because most of the time the fragile connections were only partially disconnected, so it looked like the motors were spinning normally on the ground. Then, in flight, vibrations would cause microstutters or partial thrust loss, resulting in a lot of weird behaviors and the occasional sudden catastrophe.
They ask you how you are, and you just have to say that you're fine when you're not really fine.
There were a couple times where the problem was so hard to diagnose, my only recourse was to replace the speed controllers and motors one by one until the drone started flying normally again. For a large part of the project, I couldn't even get the Pixhawk to save its flight logs, so I didn't have any help in diagnosing the issues. At one point, when I was encountering motor issues almost every single time I flew the drone, I finally decided to replace all the motors and speed controllers with higher quality ones from a reputable brand, T-Motor. even though they were a lot more expensive. I also directly soldered the motors to the ESCs this time. Lesson 6. Cheap parts are no longer cheap if you have to buy them 3 times. This reduced the number of motor problems, but it didn't solve everything. By the way, if you haven't caught on yet, 90% of the time I spent on this project was taken up by troubleshooting hardware issues. But eventually, I reached a bout of good luck with the hardware, completed my final testing, and then I decided that I was ready. It took 52 broken propellers, 7 broken arms, 6 broken legs, 2 Pixhawk flight controllers, 2 Jetson Nanos, an ungodly amount of 3D prints, and multiple sets of speed controllers and motors. But after 2 years, devastating crash after crash after crash, and countless hours of effort, the time had come for Greta to finally fulfill her true purpose. And we're off on the great dog walk of the century. Today we make history. You know what to do, Graham. You can do it. Oh. Yes! He's done it! Yes, Graham. So now I will bag up the prize like the good citizen that I am. But this time, I will not have to carry it for the rest of the walk. No, sir. Not today. All right, we're gonna move it about 20 feet down the street here so we have a nice place to secure the dogs. All right, I think this should be good enough. Okay, dogs. All right, got my trusty app out. Got all 3 green lights. I think we are go for the pickup poop mission. Our pin looks good. Okay, sending the command now. It's armed. Taking off. All right, you can see it in the distance. Rising up to 20 meters. All right, here it comes. Come on, Greta. You can do it. Flying over. Here she comes. Okay, the positioning looks okay. See the descent, giving it a little space. Oh, it's locked on. That was a perfect descent right over it. It's coming down. Come on, this looks really good. Oh my God, I barely got it. It's grabbed it. Okay, it's arming. I think it has it. Okay. It verified that it's got it. Yes, Greta, go. Fly back home, Greta. And she's off. She's off with the poop.
It's beautiful. Look at her go. Fly, Greta, fly. She's going. Here she comes. It's landing. She's back. She made it. And the bag is safely back home, and I did not have to carry it back myself. After 2 years, I had finally done it. And in case you thought that looked too easy, it was our 6th attempt and 3rd attempt that day when the dogs were long gone. Sometimes the downward obstacle avoidance would trigger inexplicably, sometimes the camera would lose connection on takeoff, sometimes the program would crash, causing the drone to hover in place. Sometimes we would be unlucky and the drone would miss 3 times in a row. Sometimes we would get lucky and everything would work perfectly. Except for the landing, leading me to switch to manual mode in a panic with the throttle all the way down. So even though a 10% success rate and the requirement for me to constantly have my hand on the e-stop at all times doesn't sound like the most practical thing in the world, you've probably guessed that a practical solution to my problem wasn't actually what I was after. So why did I waste 2 years of my life on this silly nightmare? Well, it was an excuse to learn new things. Here's a list of everything that I had no prior experience with and learned independently throughout the course of the project. And even when it became less learning and more suffering, I think it's always worthwhile to practice doing really hard things. Because I can tell you this, whatever I do next is going to seem like an absolute piece of cake in comparison. Speaking of which, if you want to see what I do next, you should probably subscribe. This wasn't the only thing I've been working on. What's that say? Of soda!